third stage. Online. Choose one problem to try.
I would like to try problem number 1. Reject.
Reject. Number 1.
Spaghetti accelerator.
1 minute.
Accept.
Accept. 13. Reject number 1. Reject number 1.
I'm ready. I'm ready.
You're ready? Okay, you can. Okay.
刚刚这个我听到发现 today I'm going to report number 13, spaghetti accelerator. As a proper statement, when a piece of spaghetti is pushed into a centrifuge, small degrees of spaghetti may be ejected from the outer end of tube and superrising with high speed. We can investigate this phenomenon. So our pre-question is the reason the factor and parameter the fact of high speed and energy distribution flow during the process. So first, these are my layout. And first, we observe this phenomenon. So we observe that the spaghetti when spaghetti pushed into the tube, it stores kinetic energy, and then when it achieves the maximum temperature, it will fracture, and the potential energy of a debris will turn into a kinetic energy. So we think that is the physical mechanism. And next, we observed the process of the pushing here. And we found that this specialization can be used the simply supported beam model to describe it, and within the factory point sinks at the point of the initial force. So before talking about theory, we're going to talk about background knowledge. So first we need to use the stress. And stress is the internal resistance for material subject to the external force. Visualize this formula. And the strain means a change in shape of size due to applied stress. And so in that formula, so we can actually tell the stress is actually related to strain. And then it's bending momentum. Bending momentum is the parameter to describe material bending stress. So it is actually related to the curvature. And before we need to use this, you will renew this beam theory. And this is a formula to quantify different other properties of the material, and this is that theory. And 5 is this is what simply supported beam structure looks like this. Okay. So first, we need to talk about simply supported beam model. So if we consider the study as a simply supported beam, then a triple study, then the bending momentum can be calculated by Euler-Bernoulli beam theory. So this is what the structure is like, and this is the we simulate this formula, and then this is the shape of the material, and you also can use that formula to calculate the bending momentum, and that is the shape of bending momentum. It should be noticed that the blue part and the red part, the middle point of the blue part and red part is the force applied condition. So as you can see, the maximum curvature is actually located at the middle force, and if we know the shape of ring, we can know the momentum distribution. And next is about how do we calculate the energy distribution. So if we want to calculate the bending energy, we need to use this formula, and it needs to be noticed that it is actually applicable to bend angle bending. And then we also have a relation between bending momentum and the curvature. So our goal is, if we know the shape of the stability, and then we will know the momentum BS position. And if we know the momentum, we know the curvature. And if we know the curvature, we know the bending energy. So we know the bending energy. So how was the stability break? So we think that with the material with the maximum curvature, it will be great, and therefore average stability maximum curvature should be same according to material properties. This means that every group of stabilities we push into it should break at same maximum curvature. And then since the stability will be separated into two parts, debris and initial part, so the energy which is absorbed by debris is only considered the potential energy of propulsion of the debris. So actually, this is the total energy. It will turn into two parts, and the debris propulsion will turn into the debris kinetic energy, and the initial part propulsion will closing the initial part oscillation. And so these are the basic flow chart, I think. So I think the most important parameters in this is potential energy and energy ratio turning into the debris energy, energy loss, and initial stability acceleration. And then I think the key point of fracture in stability is the shape of stability, but not the shape of tube, because the tube is only have a geometry condition. So if I have two types of tube and it leads to the same shape of stability, it will lead to the same physical condition. So I think the shape of tube has no physical meaning. And then it's our setup. So this is our flow chart. The blue part is actually what we can measure it, and the orange part is actually we can know by the thing that we measure. So the first we know to measure the shape of bend, stability, and then we can know the curvature, energy distribution, and then we know therefore curvatures. So we want to know whether every adjacent maximum curvatures are same. And then we will know the debris length and debris facilities, which debris length dt. We want to know whether every adjacent breakpoint is located on the maximum curvature. And then if we know the curvature, if we know the energy distribution, we can know the debris potential energy. And then we want to compare it to the debris kinetic energy. And we want to know the energy transform ratio. So in this process, we were talking about whether assumption of potential energy is reasonable, because we mentioned before we only consider about the debris potential energy. And the second one I want to consider is what is the energy transform ratio, so that we can know this portion. So this is my pushing mechanism. So actually I use a stepping motor and bearing, gear, and belt to make the same facility input. And this is a bend tube, and I push my spaghetti on my belt. And then this is how I measure the shape of spaghetti. So first, I use MSJ to label the point coordinate on spaghettis. And then I can use this data to fit curvature of the cure. And then if I know the shape of cure, and if I know the function of cure, I can actually calculate curvature. So let's move on to the experiment. So first, we must calculate the audio values. So we measure audio values by we fix both sides of the spaghetti and we apply the force on the middle point. And then we can know the curvature, the maximum curvature. So which we can know the Gauss modulus by this formula. And then we separate the spaghetti into 5 different groups. So this means that 5 different shapes of spaghettis. And yes. So need to be honest that in this state we only consider that the quasi-steady state, which means I push the spaghetti into an increased slow speed. And this is the static pressure here. So as you can see, the break length is not different, and the breaking point is actually nearby the maximum curvature. So before everything, I start to measure maximum curvature, and the dark means the break point curvature, and the arrow bar means the maximum curvature, arrow to the distance to the maximum curvature. And as you can see, this result leads to 2 conclusions. One is maximum curvature is only depending on the material properties. Because you can see, in different kind of groups, the maximum curvature is pretty standard. And the breakpoint is pretty close to the maximum curvature position where the middle force is. Because you can see that the breakpoint curvature and maximum curvature percentage error is actually pretty small. So then, you can see, this is the graph I want to show you. Because you can see the static pressure and what we are doing at. So, but in one condition, we do not go into a fracture condition because the maximum curvature isn't reaching the threshold of fracture curvature, which is about the IT. So, it actually it will not break. And then I calculate the potential energy and the energy ratio. So these are the potential energy and these are the kinetic energy. So I plot it on the graph so you can see it. So actually you can see that the potential energy and kinetic energy is pretty close. So you can know that the energy control ratio is actually close to 100%. It means that the assumption of only consider potential energy of degrees parts is reasonable. And next is we notice that the potential energy is almost converted into the kinetic energy, which means that the energy loss is pretty small. So you can see the energy rate right here. It's almost 100%. And I think the arrow comma here is just like the MSJ label point arrow. So after quasi-steady state, we do non-steady state, which means I input the spaghetti in pretty high speed. So we can observe the spaghetti become hardened, and the hardened level seems related to the facilities. So as you can see, in this means that I input it pretty slow speed, and this means that I input it pretty high speed. And you can see the spaghetti won't break until it's started. Okay, so this graph means the input facilities versus the maximum curvature, and this means the input facilities mean versus the debris length. As you can see, the curvature, maximum curvature, and the debris length go higher when I put my input facility higher. So to explain this phenomenon, we use a dynamic hardening, which means that actually the dress of the material is actually related to the strain rate from the above formula. So if spaghetti is pushed into high speed, it will actually affect the strain rate instead of A and C, and this leads to a change of maximum strain. So it will lead to a change of maximum bending momentum. So we actually plot the data and compare it to a theory. And you can see that it is actually a linear relation, and R square is equal to 0.10. And we also find the coefficient in this, the strain rate centricity coefficient is approximately 0.27. So these are our conclusions. So in our research, we found that this spaghetti accelerator actually can break into 3 parts. First part is know, if we know the middle port position, which depending on the geometry, we can know the maximum curvature. And if we know the maximum curvature, we can know objective facilities because the energy transport, the energy ratio is absolutely 100%, and we know the energy distribution. So we know that every objective maximum curvature are same, and every objective breakpoint ratio are close to maximum. And we also know that degrees kinetic energy only comes from potential energy of degrees proportion, and we know the energy transform ratio is close to 1. And on non-steady state, we found that the effect become harder while push speed become higher, and it can be described by the magnetic target formula. And the strain rate sensitivity coefficient is about 0.27 in this kind of studies. And that's my report. Thank you.
Okay. Show question of the opponent.
Okay, first, thank you for reporting. Now, does your spaghetti always eject out? Yes or no?
What do you mean?
Does the spaghetti always eject out when you push it into a tube? Yes or no?
Yes.
It always ejects out?
Oh, no. If the spaghetti didn't match the maximum curvature, it won't eject it.
Do you think the maximum curvature is the only factor that will prevent the spaghetti from ejecting out?
What do you mean?
So, do you think that if the spaghetti doesn't eject out, it will only be because of the maximum curvature?
Yes.
Okay, thank you. So, can you turn to page 6? Okay, what do you mean by the middle force?
Middle force, that means, because you can see that there are like 3 forces in the spaghetti, and middle force means the force right here on the middle point.
So how many points does your are your spaghetti in contact with the tube?
What do you mean?
Like how many points are the
3.
spaghetti?
1, 2, 3.
Okay, thank you. Can you turn to page 7? What is that? K is that?
KK is curvature.
Okay, thank you. So can you turn to page 8? Okay, so is that the? So did you say that that's the shape of the spaghetti?
Yes.
Okay, thank you. Okay, so can you turn to page 9? So, like, did you fit the shape of the spaghetti into according to the experimental data?
Yes.
Okay, thank you. So, can you turn to page 10? So, you said every spaghetti's maximum curvature will be the same. So, did you use the same kind of spaghetti?
Yes.
Did you consider that the spaghetti may not be uniform?
No.
Distributed?
No, it didn't uniform.
So, but like, maybe there will be some denser parts, or
I think that the possibility is pretty small.
so did you observe any deviations in the maximum curvature?
What do you mean deviation?
Okay, never mind. Okay, so can we turn to page like 24? Sorry, that's all.
Okay.
Okay, hello everyone. So I'm going to tell the reporter, sorry, the opponent from Team Maxwell, and today I'll be opposing on the spaghetti accelerator. So this is the problem statement. When a piece of spaghetti is pushed into a tube, the small debris of spaghetti may be ejected out from the other end as it's passing high speed, and we have to investigate this phenomenon. The reporter thinks the key points are the fracture of the spaghetti and the bending of the spaghetti. And the reporter also thinks that energy is important. So first, in terms of the reporter theory, first of all, the reporter considers the stress and strain of the spaghetti. So the reporter seems to measure the bending of the spaghetti and fitted it to his theory to measure, calculate the potential energy of the spaghetti. And so later the reporter used his energy perspective to compare it with the kinetic energy of the debris that were ejected out. And so the main focus of the theory seemed to be the energy perspective. And the reporter also explained how different input speed of the spaghetti may cause the spaghetti to harden and cause different phenomena. So for the setup, the reporter seemed to use a motor to control the input of the spaghetti into the tube. And for the parameters, the reporter considered the injection speed of the spaghetti. Okay, so in terms of the results, the reporter seemed to think that only considering the potential energy is reasonable, which I think we'll discuss later. Also, the reporter found that the fracture point was close to the position of the middle force. Next on to the strength of the report. First of all, I think that the reporter had a complete theory and an explanation. So first there was some simple graphics about the qualitative theory about why the spaghetti breaks, where it breaks, and why it ejects out. And I would also like to commend the reporter for attempting to derive some equations for the bending of the spaghetti and attempting to calculate the elastic energy of the spaghetti and separated the elastic energy into the debris and the main piece and compare them with the kinetic energy. And yeah, so also I think that the reporter had quite a controllable setup in the experiment, which I believe impacts the experiment quite a lot. However, first of all, I think that the reporter may need to consider the different ejection conditions. So the reporter only mentioned that the curvature of the spaghetti was the only reason for the ejection. However, I think that the reporter did not consider, for example, the diameter of the tube, which may prevent the spaghetti from ejecting out, which I think we'll discuss later. And also, the reporter in his report only calculated the energy loss. So perhaps in order to have a clearer picture for this phenomenon, perhaps the reporter could explain the reasons for the energy loss. And also, while the reporter did manage to fit the shape to experimental data, there were some experiments where the reporter did not fit the theory with the data. Also, which I think this is quite a large error here. So I think in one of his slides, he calculated the energy transfer ratio of the spaghetti debris. And there seemed to be an energy transfer ratio of more than 100%, which I think is rather unreasonable. And now I would like to invite the reporter onto the stage. Okay, so first of all, you mentioned that the curvature of the spaghetti is the only reason that the spaghetti will not eject out. Is that correct?
Yes.
And what is the reason for this?
Or why do okay, so just it is the only reason that the spaghetti will fracture. There are no other reason that one causing the spaghetti fracture.
Okay, so perhaps okay, what is the diameter of the, for example, if the diameter of the tube is small enough, even if the spaghetti does reach a close to the maximum, for example, in curvature, perhaps the friction on the tube, if it were too small, might prevent the spaghetti from ejecting out. Did you consider this?
So first of all, if my spaghetti is located in like this tube, okay, so the water is actually right here. So if pressure is over here, so I think the first degree will going down right here. So a dog, you think you use the kind of this kind of tube and you push spaghetti like this. Of course they want to adjust it, but because my physics models mean that we can know the breakpoint and then we can calculate the potential energy before the breakpoint. So if we add all this potential energy, so if it fracture, the potential energy will turn into the kinetic energy. So in my case,
what do you mean by of course it will not eject out?
So I mean that if of course at the break moment, the potential energy will turn into the kinetic energy. Yes, but after that moment, maybe like the force right here or force in the tube, cursing is not ejected.
Okay, so you think that the wall of the tube may cause it to not eject out, but so what I was saying was this, perhaps I could draw a better picture. So let's say this is the tube, and so even if the tube had a say great enough curvature for the spaghetti to bend significantly enough that the spaghetti would eject out. But perhaps if let's say this is the spaghetti, if the diameter of the tube was close enough to the the width of the tube was close enough to the diameter of the spaghetti, perhaps the spaghetti would get stuck here. And so do you think this will happen?
Sure. Sure. As I mentioned before, in my presentation, I proved one thing is that I proved the basic mechanism. After break,
okay, I think we'll move on to the next point. Okay, so can you turn to, I think you fitted the shape of the spaghetti.
Yeah.
Okay, so is this shape from your theory?
That is shape from my experiment data.
Okay. And so did you compare, so what function did you use to like fit the bending shape?
3. Qubit. I use qubit function to fit the shape of the spaghetti because it is reasonable to be used because I use the simply supported model in my system. I use this one. So this one is 3 terms from the panels. So I use 3.
So you use, so what you mean, what you're saying is that, so if this is a spaghetti, you fit it the shape to a 30-degree function, is that correct?
Yeah, sure.
Okay, so next, so did you calculate the radius of curvature for the bending?
Yes, repeat again.
And also did you calculate the radius of curvature for the spaghetti?
Radius of curvature of spaghetti. What do you mean by radius?
So for example, if the spaghetti was bent like this, I think it would also be reasonable to fit a circle onto the spaghetti.
So actually, the curvature is, I don't want to talk about. I want to mention the curvature radius, but actually the kappa curvature is equal to this. So is that measured? So if I know my curvature, I know my curvature radius.
Okay, thank you. And also, you mentioned you used a simple supported beam to model the spaghetti, but is the the bending situation actually the same?
Yes, I believe. Because I solved this phenomenon, I observed there's only 3 contact points with spaghetti and a tube. So if they only have 3 points, they only have 3 normal force. Apply to spaghetti.
So perhaps your spaghetti is also resting on the tube in some places, or is it just because of the picture?
The picture.
Okay, next, I want to talk about your energy transfer ratio.
Okay.
Okay, so how did you manage to, how many times did you do it?
As a group, I have different ones, but I didn't always have about up to three, more than 3 times.
Okay, so
Yeah, so I have error loss.
also, what do you mean by condition 1, 2, 3, 4, 5?
I mean, because I separated quasi static, because they have 4 different kind of bands like that, so it means 4 different kind of conditions.
Okay, so can you explain that a bit more clearly? So perhaps there are some graphics in your presentation.
So actually, I separate bands tube into different kind of conditions. So it will lead to a different kind of shape of the static. So these 5 conditions means that different shape of the static. So and these shape all lead to one conclusion is that.
Okay, so can you turn back to that table?
Table.
Yes, the table with which you listed all the 5 conditions. So from this table, it seems that you kind of changed multiple parameters at the same time, and yes, you plotted them on the same. Seem to have plotted them on the same axis. So perhaps you could try to limit the change to one parameter at a time, and to compare it with perhaps your theory, because I think that comparing this condition might be a bit difficult to understand. Also, can you come back to that energy transfer ratio page? I want to ask how you managed to get an energy transfer ratio of more than 100%.
I will explain it to an error bar because you can see, first you can see, although it's over 100%, but it just only have a little bit error. Like maximum error is only 3. So I think it's just because of energy ratio is pretty huge, and also I have some error of the statistics or the facilities. It will be into a little bit over the 100%.
Okay, so first of all, I want to talk about your usage of spaghetti because I think it might be related to this. So you use the same kind of spaghetti. How do you make sure it was the same kind?
Because I buy it in a bag, so it's a very common way to present.
Okay, so I think that since spaghetti is actually made from agricultural products, and the manufacturing process may not be entirely, for example, controlled. So I think that perhaps the spaghetti will not be uniformly distributed.
I think the error you mentioned is pretty small.
Perhaps one of the errors, perhaps some of your errors in your energy transfer ratio might be due to how the spaghetti is not uniformly distributed. Also, did you consider perhaps the humidity environment and how it might affect the environment?
They consider as you can see, so that they consider humanity is actually pretty well. So I think this humanity has a little bit not a huge effect in this.
Okay, so you didn't measure the humidity.
Yeah.
Okay, next. So you mentioned that. Okay, so how many parameters did you change in your report as you recall in the class? So just that?
Yeah.
Okay, next I want to talk about your setup. So like, how did you connect your setup to the spaghetti? I think you used a motor. Can you show that page?
So here's my second model. I use code to let my model know how many what is the rotation facility should be given, and then when it starts to run, it should be in the same rotation facility.
So yeah. So how did you connect the spaghetti to the motor? How do you move the spaghetti? So you connect.
Yes.
Do you think that will affect the curvature of the spaghetti?
What do you mean?
Okay. So do you think that using tape might affect the? Okay. So
Okay. So I mean, if you use your hand, you push the spaghetti in your band. Yes, it is actually what I'm talking about. Because your hand and the tape go at this point with spaghetti.
Okay. Thank you. I think that's all.
Okay, opponent.
Okay, so
summarize.
in my discussion with the reporter, first we talked about his experimental setup. The reporter seemed to use a belt and taped the spaghetti to it and input it into the spaghetti, which I think is a rather good solution. And however, and then we also discussed the fitting equation. The reporter used to fit the curvature of the spaghetti, and the reporter seemed to use a third-degree function. However, I think that yes, perhaps the curving of the spaghetti could also be fitted using a circle. Also, we talked about his energy transfer ratio and how his energy transfer ratio seems to be over 100%. So the reporter thinks that it is due to some measuring error, but I think perhaps he could try to improve his measuring setup a bit in order to remove this error. Also, the reporter considers the spaghetti as a uniform distributed beam, which I think is incorrect. Thank you.
Okay, thank you. Question of the reviewer.
So what's your guys' explanation on why the energy ratio is over 100%? Why the energy conversion ratio is over 100%? What's the reason behind it?
Yes, I think that's maybe a bit too much error, so perhaps the measuring could be improved.
So what would you do to improve next time to avoid these kind of errors? What can be changed to improve to avoid these kind of errors?
I think I can do more times of experiment so I can make my error bar become shorter.
Is there any parameters that can be added to determine the energy conversion ratio?
No, should be not. Only yes, should not.
Okay, does the spaghetti you have any? Okay, no. Okay, the spaghetti's length speed will be dependent on the different curvature that's provided by tube. The length of the spaghetti that is being injected, will that be affected by the curvature of the tube?
Of course, of course. The tube will affect the middle force position of the spaghettis and will lead to the fracture point. Yes.
And I think that the curvature of the tube will affect the curvature of the spaghetti.
And so do you think that the shape of spaghettis or the tube will affect the potential energy? Which will the shape of the spaghetti or will the tube curvature of the spaghetti affect the potential energy that's been stored in spaghetti?
Yes, curvature is related to potential energy.
So we're using different curvature to affect the energy that's been projected out.
Of course, of course.
Very well.
Of course, because different middle force position will turn into a different kind of energy distribution, so it will lead to a different kind of kinetic energy.
Will that changes how much energy is put in when it's being exactly broken?
We can calculate by my model. It can be calculated.
So can you what? So and also how would the different? So you address it like you guys address like when it's overbent, the energy will shoot out, right?
What do you mean by?
When the tube is overbent, the spaghetti will not be shooting out.
Actually, we were discussing about the diameter of the tube because I think the friction from the walls of the tube will affect the ejection velocity of the spaghetti and perhaps prevent it from ejecting out in some conditions.
Okay. And what's your idea of when the diameter of the tube is like closer to the diameter?
Yes, of course, it will lead into energy loss, but in my model, I don't consider radius because I want to prove my physics model. I want to prove my physics mechanism without the energy loss.
Okay. Preparation of the reviewer. give you presentation.
So I'm now reviewing on their discussion on spread accelerators. So the problem statement is that they are discussing about what's the reason of the fracture and what parameters can affect the speed and the energy distribution that flows during the process. So, well, based on the report's performance, it discusses the relationship between bending moments and the phenomenon discussion. And the series, they also use the Euler-Bernoulli beam theory to basically predict how the curvature will bend and how it leads to the sort of kinetic energy. And we try to also use the dynamic part in the theory to explain when you push these spaghettis in a non-static fashion, how it affects the energy output. And the experiment tests out different fracture curvatures and tests out both static and non-static states. And it's a very good data and analysis and provided a good data and provided a good explanation for your theory. And also quantify the bending. And for concepts that you assume that spaghetti is a completely elastic material, which might not be the case if you're using spaghetti with the Euler-Bernoulli beam theory. And then you also see the shape of the two have physical meanings, which I disagree upon. And also you did not address why the energy conversion factor is over 100% during representation. So the opponent's performance, he's pointed out the lack of parameters limiting costs, and also discuss the validation of the curvature approximation, and also discuss the different reasons for errors, and also addresses why the energy conversion factor is over 100%. And the post have a good understanding of the report and has a very some different topics in mind. And the post we focus on the series and the that opportunity to experiments. And so the discussions the first discussion they point out is that this is spaghetti always inject. And the reporters claim that they're only affected by the maximum curvature if the spaghetti is not with the maximum curvature. While the reports also suggest that diameter may also matter, which I agree upon, because as diameter becomes more close to the spaghetti's diameter, it's going to increase the contact point on the spaghettis, which will eventually lead to which will lead to Euler-Bernoulli beam theory to be not applicable. And then they discuss how whether or not curvature is the only point contact, which they also agree on if the diameter is too short, it's going to create a lot of friction and leads to the spaghetti to be not ejected. And then, which I agree on. And then they also discusses how the energy transfer ratio, which they discuss how many trials they use, and which the reporters suggest over 3 trials. And then they also try to discuss about the side factor part, which the reporters try to fit a cubic polynomial to fit the spaghetti's curvature, which I agree upon because the Euler-Bernoulli beam theory which results in that. Yeah.
Okay, time is up. Thanks. Welcome.
Yes, so now I'm going to concluding remark. So first is the presentation and our contribution. So actually, in the presentation, we find and we prove the structure of the spaghetti can be seen as a simply supported beam model, and then we find a mechanism of spaghetti acceleration, which if I know the middle force position and I know the maximum pressure, I can know the ejective facility and any kind of physical parameters in this system. And then we find the energy distribution flowchart, and we prove the non-steady state can be described by the dynamic Harden formula. And in short version, the opponent asks if it doesn't reach the maximum curvature, right, eject or not, and I say we want to eject. And I emphasize the spaghetti is quite uniform, and that deviation, they asked me about deviation, but I think deviation is quite small. So that discussion, we discussed whether to advance the curvature So I think it would not because the breakpoint of the curvature will always be same, and the underlying reason is the curvature of the spaghettis. And about potential energy to kinetic energy, the opponent talked about the energy transform ratio, and I think it's because of error. And I was also pretty small enough. And so we found the energy ratio, and we talking about some pushing method, and we got to pushing method is absolutely correct. And about the discussion more, we're talking about the community theory, and I said I used the third degree polynomial to fit my data point, to fit my shape of spaghetti, and which is pretty reasonable because my system is supported being here. And about the distribution of spaghetti is quite uniform, which I mentioned in the question. And the opponent said I can use circle fitting spaghetti shape. So, but I think it's not necessary because I can find the curvature if I know the shape of spaghetti and function of it. That's all. Thank you.
Okay, thank you. Julie, question? Any question? So, please.
Yeah, around, but how you show is you change the injection speed of the spaghetti, but the result will influence by
What is
the injection speed.
Injection speed? I didn't. Injection speed. I didn't do injection speed.
Oh, you didn't change the injection speed.
I did input speed.
Or input speed.
Yeah.
The input speed different. The result will differ, right?
Yes.
So could you all of them? Could you comment what's the reason the input speed is different will influence the result?
In my theory, I think it is because of dynamic harden, and the dynamic harden is caused by if the strain rate is different, it will cause the stress is not uniform in the spaghetti. So you are causing a dynamic harden. And but if I stop the input, if the input speed is equal to 0, like in this after it becomes 0, it breaks. So it's saying that it's not the dynamic harden.
How about
Okay, so I'll go first. So from his video, it seems that the curvature of the tube is not very significant. So perhaps the input speed also provides some initial energy, which contributes to the ejection speed.
So I feel like the input speed is what gives the energy to, is unfortunate to have the spaghetti to store the energy as bending. So increasing the speed will increase the decrease of time that needed for spaghettis to reach the bending moments, which will probably lead to more spaghetti pieces to be spit out, but will not affect the individual speed of the individual degrees of spaghettis.
Okay, another question? No? Please say. Okay. Bottom 7, 6, 8, 8, 8. For the performance, 7, 5, 6, 5, 6. For the reviewer, 5, 5, 5, 5, 5. Okay. OK，好，我已经完成这一场的比赛后。